Alright, let's look at how we calculate the pH of a buffer. First of all, let's backtrack and let's say what is a buffer. We can use two definitions for this. We can use a kind of a practical definition, then we can use a chemistry-specific definition. So, practically, a buffer is a solution which resists change in pH. Okay. Our chemistry definition is going to be a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid. Right, now, how does that work? How does that work as a buffer, let's say? All right, let's say that we have something like acetic acid, CH3, COOH. We dissolve this in water. And we get CH3, COO minus, and H3O plus. Right, this of course is our acid, this is our base. If you will remember, this is the thing that gives up a proton, this is the thing that accepts a proton. This is our conjugate base. The thing that we have left over after we've given up a proton. This is our conjugate acid. Thing that's left over after we've accepted a proton. Okay. If we have these mixed together in a solution, we throw some acid into here. It's going to react with the conjugate base. That's going to basically absorb our acid, so to speak, for lack of a better term. It's going to react with the acid. It's going to keep the pH from changing that much. Same deal too. We throw some base in here. It's going to react with the acid. All right. Now, in order to do this, in order to calculate the pH of a buffer, we are going to use an equation called the Henderson-Hasselbalch equation, which tells us that the pH of a buffer is equal to the pKa of the weak acid. Hold that thought for a second. I know I haven't talked about that. Plus, so it's going to be the pKa plus the log of the pH is equal to pKa plus the log of the concentration of conjugate base over acid. Now, this is only true under very specific circumstances. Our pKa needs to be relatively small. Our concentrations need to be relatively high, but that covers any situation we would have in this class. Right, now, pKa basically is a description of how a weak acid or a weak base dissociates in water. Okay, if we were covering this in more detail, we would calculate pKas and pKas. Right. For for acetic acid, our Ka is 1.8 times 10 to the minus 5. That's unitless, by the way. Now, to find the pKa, which there again, different thing from the Ka. Basically, it's an easier way for us to express Kas. By the way, smaller Kas mean stronger acids, smaller pKa's mean stronger acids, larger Ka's mean stronger acids. But in any case, if we take the negative log of 1.8 times 10 to the minus 5, we get 4.74, which is our pKa of acetic acid, right? Now, let me emphasize this. pKa is substance dependent. All right? pKa is substance dependent. It will have to be provided to you in this class. I haven't taught you how to calculate Ka's from information provided. But in any case, let's look at a couple different situations. Let's look at acetic acid, where our conjugate base concentration is 0.500 molar, and our acid is 0.500 molar. So pH, using the Henderson-Hasselbalch equation, is going to be 4.74 plus log of 0.500 over 0.500. pH is equal to 4.74 plus log of 0.500 divided by 0.500, which is 1. Log of 1 is 0 in any base, by the way. pH is equal to 4.74. So that brings us to another important point. When our concentration of acid is equal to our concentration of conjugate base, pH equals pKa. All right, let's mix this up a little bit though. Let's say that pH is equal to, let's say that I have 0.60 molar conjugate base, 0.40 molar conjugate acid. All right, pH is 4.74 plus plus log of 0.600 over 0.400. So we have more base than acid. Let's pause for a second. Let's think about what we would expect here. We have more base than acid. We would expect this to be more basic. Okay? Take the log of 0.6 over 0.4. We get pH is equal to 4.74 plus 0.18, okay, which is going to be, which gives us a pH of 4.91, which of course makes perfect sense. All right, let's look at a third situation though, where we have more acid than we do base. Let's say that instead we have pH is equal to 4.74 plus log of 0.400 for our conjugate base, 0.600 for our acid. pH is equal to 4.74 plus negative 0.18, which gives us a pH of 4.56. So that's how we calculate the pH of buffers. To do it, we need our concentration of conjugate acid, our concentration of acid, conjugate base, and our pKa. We just figure out what's what, plug it in, and there is our answer.